Welcome to the spacecraft. Okay, so this is where it all goes down. We didn't do that math for nothing. We're going to get out there and we're going to apply it now, like a lab, except we're going to the space station, which means there's a whole bunch of other things like radio contacts and other stuff we have to worry about. So what's going to happen is we're going to sit on the ground and we're going to configure all of our avionics for flight. We have to go through almost all of the multifunctional displays to configure them for flight and to get them ready for the journey. So what we're going to now do is begin by waking up the spacecraft. We're going to go ahead and close the cabin hatch now that we're inside of
it. Hatch closed.
And I'm going to do this again. As you all know, I'm very picky about this. And now we're going to turn on both multifunctional displays. Okay, so we're going to go through each one of the MFDs and program them. So first we're going to go into the orbit. We like the, not the ecliptic, but the orbital plane projection. So we're going to change that to the ship. To start, we will put the distance in altitude, although that may change later. The frame can go ahead and stay ecliptic. Doesn't really matter, though. In fact, you know what? We're going to go equatorial instead. And now what we're going to do is press TGT, which stands for target. And we're going to target a spacecraft. Can you guess what it is? It's the International Space Station. This is an image of the International Space Station's orbit as compared with ours. It is not elliptical, it's nearly circular as indicated by the low eccentricity value. However, it is greatly inclined with our orbital plane. If we changed the frame to the target, I'm not sure if that's possible. It's not. Okay, if we change the projection to the target, it will look circular. And that, there now you can see, is the image of the target. But we're going to target ourselves, and we're going to manipulate this frame. So the goal is to try and line both of these up concurrently, and at the same time be at the same position along the orbit. That will allow us to dock. We now go into the surface. We're going to do ground speed, which is good. That is all set. I'm going into the map now. So now what we're going to do is we're going to target the ISS through the mapping software, and that will give us a current position of the ISS. And good gosh, it looks like it's almost above us. In fact, we can see it. It is slightly southwest of us. So about this direction. We can't see it though, because it's in the day, but it's somewhere up there near Mercury. So that gives us these positions here. And these two numbers are the latitude and the longitude that we are going to be looking at. Apologies if I'm shouting. That we are going to be looking at when we take off. And those numbers that we calculate when the plane passes through the Kennedy Space Center is when we take off. Right now, so we return this to nearly the top level here. We're then going into the HSI is not of concern. The VOR VTOL is not of concern. The docking MFD is. So what we're going to do is we're going to look up the International Space Station's transponder. And the transponder is a radio beacon that just says, I'm here, I'm here, I'm here, I'm here. That's all it does, is it screams its position. It literally says, I'm here, come and find me. And that's exactly what we're going to do. So in order to configure this, we need to access it through the ComNav radios. These are set for the runways, but we're leaving them. So we're outbound, we don't care. So if we're lucky, if we tune into 131 and 30 megahertz, okay, we can't receive it. The transponder isn't that strong. In addition, it's about to set over the horizon anyway, so it doesn't really matter. But we cannot receive it yet. We won't get it until we get close by. That's the whole point of the rendezvous, so that we can get close enough that we can use the transponder. Next thing we're going to do is look at the docking port. All of the docking ports are free, so we're going to go with docking port number 1, which is 137.40 megahertz. So 137.4. And that's set now, so we go back into docking. There's nav 1, nav 2, nav 3, and nav 4. We're going to keep it on nav 1. If you press VIS, that stands for visual approach. I don't recommend doing that, and we're not going to do that. So now the docking is done. Okay, now this will be very, very important. This is the aligned plane, or the planar alignment multifunctional display. What this does is, remember I told you when we take off, we have to take off in the direction of the ISS, not the equator, because we're not concerned with getting into orbit anymore. We're concerned into getting into the ISS's orbit. And in order to do that, we need to take off in the direction, which in this case, if we were in Cuba, we would be taking off in the southwesterly direction, parallel to the ISS as much as possible. So we do that right now, target the ISS, and now you can see we have a monster, 51 degrees of inclination. If I tried to do that with a planar alignment burn, I would run out of fuel. No question about it. Absolutely no question about it. So we cannot have that. So the way we lower that is simply by turning into the orbital plane. So when we turn into the orbital plane, I believe we are at 330. When we turn into the orbital plane, we will be traveling in the plane, so we won't worry about that. So basically what we do is we take off and we turn east until the R-ink counts down to either 0 or as close as it gets to 0. And then hold rate at 0. This is changing because of the Earth rotating. But we try as best as we can to hold this at 0 as we climb. And then later on we might have to do a nodal burn in the direction of a plane change burn, which is rather expensive. And the most important MFD of all is going to be the sync orbit MFD, which needs a circular orbit to be configured properly. So I'm not going to bother with that now. Transfer is unnecessary. It's a redundant function. The COM and NAV radios have been... Can I change... Oh my gosh, I can change my transponder frequency through this. That's cool. I don't want to talk to you anymore, Spud. Bang, 109. But no, we're going to keep it, and that is set. So we're going to turn off the music, and we're all set. So now we prepare for takeoff. We're going to go to our surface, reset this back to 2. We're going to turn our air flight control surfaces on, increase our elevator trim, and activate the HUD, and change the color to the atmospheric one. So this is it now. We sit on the ground for a very long time until we wait for a launch window to come around. And I say it's a very long time because I know it's going to be a very long time. You're going to see these lines will be progressing west and west and west and west, and then eventually these ones over here will start drawing closer and closer and closer. It's going to be a long time. So we might as well go up to maybe even 10,000 time acceleration. Accelerating now. 10, 100, 1,000, 10,000. And the sunset Okay, slowing down, back to 100, back to 10. Sorry about that. Okay, I don't like the idea of taking off at night, at least for now. So we're going to keep going. We're going to fast forward through the opportunity. But I'm not going to pause the video so that you can see the opportunities as they go by. Ooh, shoot, no! Ah. I just missed one. I was going too fast. I shouldn't use 10,000. We're going to cheat now. Go back. It's 4 o'clock? No, I don't think so. Last I checked it was like 12. Hey look, it's 12 again! I wonder how that happened. I wish real life were like that. Okay, a launch window has been determined. As I zoom in, you can now see this line here passes very close through Cape Canaveral. And this is going to be the angle that we use. And now we need to calculate this angle. So give me 1 second to figure out how that's going to be calculated. Okay, so I figured out how it can be calculated. What we're looking for is the slope of this line at this point. This happens to be a sine wave. Thus, we can use simple calculus to find the slope. So we have a sine wave, and we want to take the derivative of a sine wave at a point to get the slope of the line. We need to find out what the longitude of the ascending node is. Okay, so it's not this orbit, but it's going to be the next one that goes over it. So this is it right here, and lucky enough, I think that's the equator they're passing through Indonesia. What is that, Jakarta? Dober. Okay, so now what we're going to do is look up where Doberi is. Yes, it's near the equator. So I'd say it's fairly safe to say that 133 degrees east, 133 degrees east is going to be the oh geez, where the ascending node crosses the equator. Yeah. Good thing the Earth rotates around its equator, because then I'd have to do it again. Okay, so that is it then. 133 degrees, and turn tracking back on. We are at 80 degrees west. So we need to find the difference between 80 and 133, which is going to be 80.7 plus 133. And that leads for a phase angle of 214 degrees. And now we're going to take the derivative of sine to get the slope at this point in the line. The derivative of sine of x is cosine of x, so we're going to do the cosine of 214 degrees, which is, hang on, is that what we wanted to do? Hang on a sec. Yeah, I think that's what we wanted to do. So we get this thing called negative 0.83. And I have a hunch that if we put it into arctangent, we should get a number. And we get negative 39.6. And that sounds reasonable from the origin. And thus you have it. So we're going to add 180 degrees. And we get this angle equal to 320 degrees. So now this angle that we have discovered is the angle of the intersection of the inclination, or the AII, or whatever we were calling it, equal to 320 degrees. We now can solve our math problems. So I'm not going back to the board. I'm going to shout out everything that I do as I do it. So we now know the S. So we do S over R again, which is 2,999 kilometers over the radius of the Earth, 6,371.4707 radians, times the 180 divided by pi, leaves us with 26.97 degrees. And I think this number could be quite easily simplified. So we have 26.97 degrees. Cosine of 320 degrees yields the longitude difference. 26.97 degrees sine of 320 degrees yields the change in latitude. So we have 26.97 multiplied by the cosine of 320. So then we get 20.66 change in longitude, and a 26.97 times sine of 320 degrees for a latitude change of negative 17.34 degrees. We could check our math later when this distance, oh yeah, it doesn't leave the distance value, so hence that's why we go by latitude and longitude, is because we don't have distance tracking. Because how can we track it? Good thing we did the math, because then we wouldn't know when to take off. Okay, so we have that now, and we subtract to find the position. So it will be further north at, where are we now? We're at 28.6 degrees north, plus 17.34 degrees, which means when the ISS is at latitude 49.94 degrees, we take off. And similarly, we have 80.7 plus 20.66, meaning the ISS, when it is at 101.36 degrees west longitude, we take off. Which means takeoff is at this number here, 101.36 degrees west, and this number, 49.94 degrees north. It won't be exactly that, but when it crosses through that, we hit the gas, and that is our takeoff time. So we've done it. We have a time for takeoff. We're now about 135 minutes from takeoff now. So I'm going to pause the video for about 2 minutes, while I mentally prepare, go through all of the stuff, make sure that, everything is set. So I will see you guys soon. Okay, so we forgot to turn the lights on. We're going to go ahead and turn strobe, navigation, and beacon lights on. And now we sit here on the pad in the morning waiting for that time. And we're going to go slow with the time acceleration so we don't miss the launch. We're approximately 90 minutes now from takeoff. You can see the Terminator, which is the sun, sunlit portion of the Earth slowly moving around as the time goes by. 45 minutes from takeoff. "30 minutes from takeoff. I'm now slowing down to 10x. We are keeping an eye on these two numbers here. I'm looking at the longitude first because it's going to be changing faster when it's up here. Here comes the ISS now. One thing I need to mention before it gets too late, the calculations we did were not the kind that you can use in real life. When you're doing that kind of stuff, and you could be in high latitudes either, you have to take into account that this curve turns. I haven't taken that into account. We'd have to transpose that onto a sine graph in order for it to work. And I'm trying to keep things as simple as possible. I feel like they're already out of control, difficult. It's only rocket science, though, so don't worry about it. Okay, this is ticking down now. 130. Okay, we have full tanks, nearly full tanks. This is it, final countdown. The ISS is coming overhead. There now you can see 49 degrees was already surpassed. That's because this line is not straight. I'm now down at regular time acceleration. You can see the ISS is moving very, very rapidly across the landscape. And that's because it's moving 8 kilometers per second, which is insanely fast, but we're going to do that too. Okay, we're at 113. 113 and counting. One 12. 111. One 10. 109. If you don't care to watch the final countdown, you can probably fast forward a minute. I'd say we're probably exactly 60 seconds from takeoff or launch. 108. $107. 106. 105. 'The ISS will any minute now be coming up overhead about here. 104. Okay, I'm getting ready for takeoff now. I have my hand on the joystick and I am beginning to prepare for flight. 103. 102. 'Final countdown. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And that's it.
9, 8. Ignition sequence has started. 6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff.
In real life, because of human error, they would have this programmed. That is rotation velocity, liftoff, gear up. Throttling back. And now
Gear up.
we switch off of the map MFD to the aligned planes. This is it. This is where we want that R Inc to count down. We want to try and get it as low as we can. Keep an eye on the map as well. And there you can see now the green lines is our orbit, which has recently formed on it. Okay, I'm going to engage full power again. And so what I am doing now is getting the relative inclination to count down. And then what I'm going to do is turn into the orbit before it's too late. So we're ascending now up to 30 degrees. I'm now going to turn back to parallel the orbit and to stop the R-Inc from changing rate. There's 10 kilometers. 13 kilometers. Apologies about that. Okay, so we left off a little bit. Sorry about that, but stupid recording. Okay. All right, so we have done almost everything that we could do here. We're going to now let that count down. We're approaching 1,000 kilometers, and we're now at 24 kilometers. So we're coming up on the ISS rendezvous right now. Because the sun is on the east, the ISS is on the west, and it's daytime, there's back to our service MFD. We're going to see if we can find it. Should be up there. So we're going to need to go a little bit higher now. So basically the goal is to try and get it that the rate stops, which is when your engines turn off, and the inclination reaches zero at the same time. If that happens, then you've done it correctly. And if not, then well, then you haven't, and you waste a little bit of fuel. It's nearly directly overhead. We should be able to see the ISS by now. I don't know why we can't. Okay, our dynamic pressure is ridiculously high now, so we're going to go up a little bit more. We're now at 31 kilometers, and now I'm going to counteract that because we're going to get joisted out of the atmosphere, and we don't want that too quickly. Well, I'm going to stop looking for it now because that's just going to waste time. 2,000 meters per second. The ISS should be passing us by now, which is normal. Should be up here. That's normal, though, because the rendezvous works that we get there faster than the ISS does because we're lower down. So that's basically how that works. And you'll see when we begin to use the sync orbit. Use a little bit more upward trim so that we can accelerate a little bit faster. 2,800 now. You can see now these lines are nearly parallel, which is good. Hopefully we won't pass that, so we can save a lot of money by doing that. There's 3,000 meters per second. Okay, so the ISS has passed us, again, normal. So now what I'm going to do is go to the orbit. I'm losing altitude. What the heck? Okay, well at least I'm burning fuel, because that would drive me crazy if I wasn't. Okay, we now have less than 4 degrees of relative inclination. Now our small orbit, the green line here, is starting to form around this big one here, which is the yellow one with the ISS. And what we're going to do is try and get ours to meet its somewhere along here, using the sync orbit MFD, again, could be calculated with rendezvous formulas, but we're trying to keep this simple. The goal is to try and get the two paths to cross and our positions at the same time to be in one location. If we can pull that off, then we can do it. 4,000 meters per second. So we are now at approximately 300,000 feet. So the sky is basically the blackness of space. You can see as well the density and pressure are as well counting down. So I'm going to add a little bit of more upward acceleration here. So we can get positive vertical velocity. That's 5 kilometers per second. There's 6 kilometers per second. Okay, now this is where I'd be hoping we're going to do main engine cutoff, and that is when we're perpendicular to the ascending and descending nodes of our orbit, as or the plane aligned with the ISS, because that will make the plane changes as cheap as they could possibly be. So that's what I'm aiming for, is getting these two perpendicular before rate goes positive. Okay, 6,500 meters per second. Now what I'm going to do is wait for main engine cutoff to occur when two things have happened. One, the apogee has swung around, and two, we get an upper intersection with the ISS. As soon as the green line crosses at apogee with the yellow orbit, which is the target ISS, I perform main engine cutoff. 7,000 meters per second, this is it right here. This is when I want to cut my engines. When this goes positive, then I don't like it because I end up wasting fuel. I'm going to release elevator trim now. Okay, I'm watching this apogee now to swing around. Okay, it's beginning to swing. There it goes, and it's getting closer, 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 crossing. We have intersection. Main engine cutoff. And now you can see our rate is 0, and we're about 1.88 relative inclination. I'm very proud of that. We're very close, and I think that was as close as we could have got it, given the current situation. Else, if it was closer, In addition, the final velocity that we were looking at was 7,600 meters per second. We were 70 meters per second off. I'm, in addition, proud of that as well. You can see we're trailing behind the ISS by about 2 or 3 degrees, and we're both in view of each other. And look at the two ground tracks, nearly the same, and the two orbits, nearly the same. And now the ISS doesn't look all bulby-like. It's circular, like it's supposed to be. Ooh, and where are we? Congo? Bridgetown. Where is that? Oh, no, Venezuela. Okay. So Kourou is probably somewhere down there. Okay, we're in orbit now. So we need to go into an orbital checkout phase now, which is going to be quick. But we're in space now, so we're going to change the color to my favorite green. We go to the orbit HUD. Take off the inefficient air flight control surfaces and onto the rotation.
Rotation.
And I'm going to activate the prograde autopilot so that we can begin maneuvering. And now you'll be able to see the Earth off to the left side as we stabilize and our climb out. That really is beautiful. Okay, so we're in position now. We're going to go ahead and also deploy our radiator, like I said earlier. And basically what the radiator does is allow our system components to cool off because there's no surrounding air for the spacecraft to bleed energy to. So we open this radiator, which cools the system components, mainly the computers and life support systems, which of course aren't simulated on this model. But
Radiator deployed.
you go to the higher advanced models, like the XR2, if you don't deploy the radiator, you will die. I'm serious, you will die. And rightly so. Okay, all of our lights are on. We're in the proper control mode. This completes orbital checkout. So, we're now going to, we're looking at our planar alignment. We're still about 20 minutes away from our nearest planal alignment maneuver. So now we go to the synchronization, and we set that up. So we're going to target the ISS, and we're going to target intersection 1. Now this is saying that our inclination is off, and right now it says that we are going to let me see what this is saying. Ship to and target to. Oh shoot, so the ISS is actually going to beat us. Let's see what the intersection 2 looks like. We can... So basically what I'm looking at now is these two values, and this is basically the lower intersection when we go back inside the orbit of the ISS. And I'm looking at this, and that basically says in 2,258 seconds we're going to get here, and in 2,187 seconds the ISS is going to get here, which is bad. That means it's going to beat us. And I'm going to use a little bit of translation just to confirm that. Yeah. That kind of sucks. So we were a little bit late, but that's okay because, well, if you can't do it in one orbit, you can just do it in more orbits. So, now what we're going to go ahead and do is fire main engines and make the intersection bigger until the DT min counts down to a match. So I'm going to go ahead and fire main engines, and we're going to look for an intersection. Oop, there's one getting closer. I also need to check on the perigee. Our perigee is here. Okay, so what I'm doing is going to raise the perigee. We should be alright. We might have to go for a low pass, but I think it's going to be alright. So right now we're looking at this orbit 1 right here. I'm going to increase the time period until these two times match up. So we're going to go back to the planar alignment, which is next. We're going to continue a slow burn. Getting close, getting close. That's it? That's it. Okay, we're now going to trim using translation. And this will maneuver about as our orbit perturbs. There we now go. So we'll be 1/10 of a second off from the ISS out of position after 1.5 orbits, which is close enough. Unfortunately, that means it's going to be about 2 hours of waiting. So we go back to rotation now. We're going to go off the attitude control. So now what we're going to do is a planar alignment, and because we're at the descending node, that means we're going to turn orbit plus. If you don't understand why, watch my orbital mechanics tutorial. And we're looking at this estimated thrusting time. And the way acceleration works is you because derived from calculus, you fire your engines 1/2 of the time that it takes you to thrust. So when this says not 16.12 but 8.06, that's when we fire our engines. And this little indicator here that says kill thrust will begin flashing burn orbit plus, and it's basically telling me burn now if I want to get my inclination down. And that's what I'm going to do. So I don't have to calculate this one. This MFD takes care of it for me. That's the whole point of this technology, is to make life simpler. So I'm going to induce a little bit of plus y acceleration, and we're going to drift up to the orbit plus as we move to the descending node. So there we go, and I'm going to go to 10x time acceleration. Doing a slow maneuver such as this saves fuel, which is always good. So now we're approaching that. So I'm going to go ahead and go here and temporarily kill rotation for now. And then go back to 10x, and we're going to wait until we're about 60 seconds from the orbit, and then we'll go back to 1x. You can already see this is perturbed above 1 second, but we're going to fix that. "300 seconds. You know, the interesting thing is the Earth is down here, but we're in no way concerned with our position on the Earth. We're only concerned about where we are with the ISS because we're a closed system now. It's kind of like a dance. Okay, that's 100 seconds now. Okay, we're about 69 seconds away from the burn. Less than that, actually. So we're activating the Orbit Plus autopilot now. What we're going to do is we're going to burn until the relative inclination is 0, which means we're in the same plane. Oh dear. I accidentally hit the gas. And our orbit's paths will cross, which means we're going to have to do collision avoidance, naturally, because we're docking. Cool, 7665. Special number for Norsden Land. Okay, so 8.07 is when we activate the engines. I'm firing at 9.07 because it takes me time to throttle up. 3, 2, 1, now. You can see the relative inclination is counting down. I don't know why this bugged me about it yet. Okay, we're getting close, 0.6. Is that it? Okay, that's it. We've done it now, 0 degrees relative inclination. That's exactly what I was trying to do. So we're now in the same plane as the ISS. And this needs to be refined now. We now also need to check up, we won't go back to aligned planes anymore, that's done. So I'm now going to check up, hang on a sec here, this didn't program correctly. Section 2, there we go, okay. Okay, we need to check out our, that's a really low pass. I'm gonna fix this at apogee because I really don't want to go this low. That is a really low pass. So we're gonna go ahead and kill rotation back to 10x. So now what I'm waiting for is the apogee to come around so that I can do a forward burn and increase the time to the intersection. And this is done by making the orbit higher, or the orbital period longer, and it takes us longer to get here. We're going to be up here for a while. I said it was going to be short. It's going to be long now. That's like 12 hours. You can see we're slewing now. That's because we're so high now that nothing is affecting us. I don't think we've come up this high before. We're at 460 kilometers. That's really high for anything that I've done so far. 5 minutes from apogee. Okay. 5, 4, 3, 2, 1, back to 1x. Okay, we're 795 kilometers from the International Space Station right now, which I don't think is enough to talk to it. 45 seconds now, so I'm moving back to prograde. So now what we're going to do again is burn prograde until DT min gets back low again to 0. I'm a little bit worried we might not actually be able to accomplish this, because if our perigee goes outside of the orbit, then we don't have an intersection anymore. There's 10 seconds now, so I'm going to begin burning. Oh dear. So it was the other way. Okay, I'm going to open up the retro doors right now. We're going to do a retrograde burn. Retrograde burning now. Wait, but I can't do a retrograde burn. We're going to go into the atmosphere. We're going to have to fix this around the next pass. I can't go back into the atmosphere. We're going to deorbit. Back to 10x.
Translation. Rotation.
Okay, I thought maybe it would say the voice in high speed. That'd be funny. And most of orbiting is just basically waiting for something to happen. So, you know, we can like look at the stars while we basically wait for us to get around the other side. I can tell you now that's the constellation Scorpius. Yep. Oh. Looks like we've just come around the, oh no, we're over China now. Oh, wait, no, that's Taiwan. I guess we were over China. Maybe not now, because Hong Kong is there. So we went south of China. Alright, I don't normally do this, but because the altitude is going to get low, I'm going back to surface. In this one case, we're trying to do it quickly, so I don't mind the low pass, but normally when I don't give a crap about how long it takes, you know, I'll spend 12 or 15 orbits sinking, and then I don't care. But in this case, we're going for a low pass, which means we need to prepare by doing things like aligning with our prograde, because a low pass means the air is going to come back again. So we need to align with prograde, and we're going to need to shut the radiator. And our orbit will perturb. Hopefully enough that this goes back to 0. Okay, 160 kilometers. This is where the atmosphere begins to be noticeable again. You can see there's a dynamic pressure now. So I've gone back to orbit prograde. We're going to go like this down to about 100 kilometers. When we get to 100 kilometers, I'm shutting the radiator. Uh-oh. Lagged a little bit. By the way, orbital sunrise. Okay, this is at 100 kilometers. I'm shutting the radiator now. just so I'm not encouraged to mess around with this, I'm going to go off of it. Because there's nothing we can do now.
Radiator retracted.
Okay, so the radiator's in. Our dynamic pressure's going up. I'm now turning into our prograde direction now. I'm trying to make myself as aerodynamic as possible so that I don't perturb the orbit. If I were a satellite, I would be blowing up. The only reason I can go down this low again is because I'm a space plane. I don't like this. This is 100 Pascal. If we see an acceleration that's negative before perigee, we're going to have to add a little bit of speed boost. I don't expect that we'll be low enough to hear the hum of the atmosphere. It's not going to be a roar, it's going to be a hum. I don't think we'll be that low. Hopefully not. This looks like glacial deposits or glacial sediments. Might this be Kamchatka? No, actually, it's California. Wow. Okay. Oh, wait a minute. Those aren't glacial patches. Those are the Cascades. I'm going to bring our pitch control back because this is a really low pass. It's kind of like coming back in. If I go too far down, of course, I'm going to slow down big time, and then I can't keep up with the ISS. That's not good. We're approaching almost 1 kilopascal of dynamic pressure, which I don't like. I really don't like that. Okay, we're now over 1. We're also beginning to decelerate, so I'm going to keep an eye on the speed. 7685 now. So I'm going to be going 7690 at perigee. I'm going to accelerate us up there using the engines because we're going to slow down. I'm going between 10x and 1x because I don't want the tutorial to be too long. Here's periapsis, so I'm going to give a little bit of main engines there. Just accelerate back a little bit. That should restore our altitude. So now we're climbing back out again. 75. When this gets under 1, it'll be better. Okay, so it's under 1, 9, 8, 7, 6, 5, 4, 3. Okay, we're back at 82 kilometers. Just going to go off here. Return to the orbital position. X. 100 kilometers. We can open up the radiator again and then go back to prograde orbital. Let's see what the damage is. It's not that bad.
Translation.
See which direction we need to burn. Ah, yes, that's what I figured.
Rotation.
Yeah, so we're going a little bit faster than we need to right now. I'm not going to do
Radiator
anything
deployed.
because there's still some dynamic pressure left over. Although it's almost gone now. That will decay the orbit to some degree. Once that decay stops, then I'm not going to be so concerned with it anymore. And we'll go ahead and do the burn. Okay, we're at 125, so we should be unaffected now. We're going to go back to the sync orbit now and complete the maneuver. We're going to do this using the translation boosters. And we're going too fast, so we're going to slow down by doing a retro burn. That was a long burn, but we did it. So hopefully that won't change around too much because we're coming up on Rendezvous. We're 250 kilometers from the ISS, which means, I mean, gosh darn it, that thing has to be visible now. It just has to. Well, okay, no, never mind. The sun is over there, so we're seeing the nighttime side of the ISS. Never mind. It's already decaying as right on schedule. Let's see if we can get the still no signal. We're too far, but we're going to get really close around this next pass. So we're going back to 10x again. And I know it seems like, I'm making this longer when I could just go to 100x and all that, but I'm trying to be very conservative and very careful about how I spend my fuel and spend my time. And I don't want to make mistakes. So I'm taking it very slowly. My first time, I took it very slowly. So slowly that I didn't even use any time acceleration until I went to the moon. That meant orbits were real time for me, and I could actually get a feel for how long these maneuvers were apart. We're back high again. Actually not that high, 225 kilometers. So we got really close. By the time we get to 400, we'll be really high. And I don't mean that as a pun. Okay, we're now at a quarter pole. So I'm going to go ahead and refine this now. As we get closer to the rendezvous position, it takes more engine power. So I'm opening the retro doors. Oh, this is going to be a prograde burn now. There we go. Orbit adjusted. A relative inclination has accumulated. But I'm not concerned with it because it's so minute, and the node of crossing will be about here, which is close enough that we can just do some translation and be done with that. Alright, so this is the final countdown and rendezvous. We're 125 kilometers, so I'm going to leave the orbit MFD. We're now going to go to the docking panel, and we have a signal from the ISS. We're now at 288 kilometers, which is high enough. I'm going to come off
Rotation.
prograde, go to rotation. I'm also changing this as well. And we're going to face the ISS and prepare for the rendezvous. Somewhere in here is the ISS. Still not yet visible, probably because we're on the nighttime side of it. Going back to 10x. This shows our relative velocity with the International Space Station. I basically have to keep it around this area in order for me to continue closing in on it. So we're going to go ahead and kill rotation now.
Translation.
We're going to go back to the translation. And we're still 0.2223 seconds away from the rendezvous, so I'm going to refine again. Done. So basically, whatever I'm doing, I'm just using the translational
Rotation.
thrusters given in the tutorial that I did earlier to move around. 350 kilometers now looks super high because how low we went. Also, we're gonna meet that at night, which makes me angry. I hate docking at night, especially the first time. But well, you saw the Mir docking today, so what the heck. Okay, we're closing in. Now we're 99 kilometers from. The ISS is now visible. You can see this dot here is now the ISS. So we are closing in. This DT min isn't moving. So this is it now. It's basically we keep moving until whenever we meet the ISS, which is supposed to be here. So that ends the orbital segment of the maneuvering. Everything from here on out is going to be translational. So I'm no longer concerned about the difference in our orbits. They're pretty much the same. The only thing that I have to do is upon arrival at the ISS, kill the relative velocity, and that's all that's left. I'm going to fix the what you call it. Whoops, wrong one.
Translation.
Yeah, the translation. I'm going to fix that now. So basically what I'm doing is I'm trying to stop the that residual. There was a little bit of residual. That's done it now.
Rotation.
There was some residual plane alignment change, relative inclination that I was taking care of there. We're getting very close now. Okay, there's 10 kilometers. All right, what I'm doing now is turning around. We're going to do a retrograde burn to match our velocity with the ISS. And we're going to assume that our engines can fire at, we'll say, wow, we're actually running out of fuel. We won't run out, but we're low, let's say. Lower than half, which is more than what I'm used to. Okay, so you can see the time here counting down. 122 seconds. Let's say that takes us 10 seconds to do that, which means we start 5 seconds before. And the distance formula is 0.5 times g, which is going to be 15, times t squared, which is 5, which means we want to start decelerating. Hang on a sec, that's not right. T5 squared. Okay, so for some reason 5 squared is 500,000. I don't know why that is. Let's try this again. 5 squared times 0.5 times 15. Okay, so 187 meters, or about 5 seconds before. And we're basically going to slow down now. And we basically do this until the V relative says 0, 30, 20, 10. That's done it now. We're in the exact same orbit as the ISS. Velocity has been killed, and it's just translational. So we're on rotation. I'm going to face the ISS now. We're just over 2 kilometers from it now. You can't see it because we're on the nighttime side of the Earth, which means there's no light whatsoever. I'm going to take this opportunity now to open the nose cone. You can't see it well because it's the nighttime side. But our nose cone is opening now. I can see now this is probably going to be like
Nose
a
cone open.
super long episode. That's just the way I am. I'm just, one of those people who it's rocket science for whatever's sake. So, I mean, the fact that it's rocket science says that it deserves a lot of attention. So we'll just leave it at that. Okay, we should now be in range. We are in range of the docking transponder, and this will basically hone in on our transponder and provide us with information on where the dock is. So now what I'm going to do is I'm going to aim for this box right here on the ISS. We're going to throttle up to about 15 meters per second, and then we're going to cruise in.
Translation.
So we've just done a
Rotation.
translational maneuver to come towards the ISS. When we get within about 900 meters, you should start to hear the radio squawking at me, telling me that we're getting close. Their docking light is on. Our nose cone is open. Sync orbit is no longer of concern. And we have the docking fully configured. So we're ready for contact docking. There's the radio squawk, and it's going to continue getting higher frequency until we get super close to the ISS, and then it's basically going to chirp and tell me, you're going to hit it, but I want to. Just very lightly. And I don't have information on where these boxes are, so I'm going to have to use my own derivative calculative behavior in my brain to try and guesstimate where to brake. So let's just get an idea for the retro engines, which are not as powerful as I thought. So we're basically going to aim for one of these boxes. We stop in the box, align ourselves with the tunnel, and then we go down it. So we're going to go ahead and brake now. Whoop. Oh dear. Okay.
Translation.
Needs a little bit of translation here to took a little bit longer than I wanted. Okay.
Rotation.
So now here's where we go back, switching between translation and rotation. So now what you're going to see is this green circle, which represents the difference in angle and the difference in distance that we're allowed to be for the certain spacing that we have between us and the ISS. And soon you're going to see a white crosshair come across the screen, which shows, there it is, it's red now, and it shows you how acceptable our facing direction is. So we're in the boxes now, which are a set of tunnels. We're directly upside down now, as indicated by this red arrow here for the third dimension. So we're going to go ahead and realign. And I'm going to do whatever I need to do to get that white X to center and the red arrow to become white.
Translation.
So now I switch back to translation. And we're going to move towards into position. Now, because our thrusters aren't perfectly mounted, we are going to get a little bit of slewing,
Rotation.
which I have to correct every once in a while.
Translation.
Rotation. And we're also going to get problems with torque, gravity gradient torque, and magnetic torque, and air drag, and a whole bunch of other things that cause the orbit to perturb.
Rotation.
And our position, for that matter. So now we basically continue repeating this procedure. I think 5 meters per second is an acceptable velocity for how far we are now. Our distance is located here in meters, and our velocity here in meters per second. Again, the box here represents the rotational along with this arrow, and then this orange cross represents the translational. We're going to slow down now, 3 meters per second.
Translation. Rotation.
That represents the other thing. Okay, now we're coming in range of the light. And then the arrow here, the orange arrow, indicates our... Whoops.
Translation.
Indicates our direction. Our tending direction.
Rotation.
Just do a little bit of readjustment.
Translation.
There.
Rotation. Translation.
So even though the lettering is upside down, we are right side up. So no worries about that.
Rotation. Translation.
Any minute now, it's going to chirp at me and tell me, hey, you're about to hit. There it is. Okay, final approach. We're going to close the retro engines now, and main engines are off limits. This means we're using translation for the remainder of the...
Rotation.
For the remainder of the approach.
Translation. Rotation. Translation. Rotation. Translation.
Docking velocity is going to be under 10 centimeters per second.
Rotation.
So basically, So basically what I'm doing now is whatever I need to in order to get the values here to align.
Translation.
Okay, I'm going to slow to 30 centimeters per second. Okay, so now that's going to go out from sight under us. So we're on visual only.
Rotation. Translation.
Three meters. Going down to contact velocity, 10 centimeters per second.
Rotation. Translation.
Performing the last maneuvers now.
Rotation.
This other way.
Translation.
Okay, contact.
Houston, we show capture and hard dock. Congratulations.
Congratulations indeed. We have docked. We have successfully docked with the International Space Station, meaning that we are the International Space Station. So we can go ahead and clear all of our targeting information now. We can't clear that, but that doesn't really matter. We are the orbit. No target to synchronize, and no target for this as well. And I'm not sure why I had Havana targeted in the first place. Okay, so we're here aboard the International Space Station now.
Attitude off.
I have to turn the attitude and control services off because once you become part of the ISS, you're now technically them. I've basically merged the two entities, so we're going to go ahead and set these off now. Radiator stays open. Our docking light can go off now, and plunged into blackness. And we can turn all of our other lights off because the ISS doesn't have those. And you can see the remainder fuel that we have now. And we're going to open the airlock now. That's the last step. So we're going to open the outer door. The ISS, this particular version of the ISS does not simulate the inside airlock, so we would have just already assumed that they've opened their airlock. So we're going to open the outer door of our airlock, which you can see if I go in between the model here. You can now see our airlock door is opening.
Outer door open.
So the outer door is open. And if all is well, I'll be able to open the inner door as well. And we're not dying. That's because the air is shared now.
Inner door open.
So now you can see, our doors are open, and you can see into the International Space Station. So that's it. Orbit, and here we are. After docking, we are over, looks like Southeast Asia. Let me just confirm that real quick. Let me see. That's going to be... Yeah, I think we're over... that's China, I know. Okay, I guess we're over Western China then. Okay, but here we are at the International Space Station. Successful docking. Next episode is on re-entry, and this is Dr. Aeronautics saying, happy docking, friends. And I will see you guys next time. Bye.